Hi folks, this is Karim Rao for IT Visualizer channel. We will continue our lab, the matrix labs, the video number 141. We have been discussing in the previous video the following. While still working with troubleshooting Windows using Microsoft Sysinternals suite, we are still following the cases that was created or that was discussed by Mr. Mark Rosenbench, the author or the creator of the tools of the Microsoft Sysinternals suite. These cases was published in his PDF troubleshooting using Windows Sysinternal tools. We have discussed about 42 cases. We have left, or we have 3 cases left, and then we can close this subject completely. Let's go and see these cases, and actually it is re-explained using AI tools, especially the tool called Claude 3.7 Sonnet. Let's see, and actually I have already added the extension of thinking, so this is an AI tool in the thinking mode. Okay, let's go and see the case. So here we're talking about the case of the unknown NTLM communication. Okay, again, this is a learning dialogue between a senior IT, which is Sarah, and the junior IT, which is Mike. So let's see this. Yes, the case of the unknown LTLM communication. This is relevant for security conscious organizations that want to minimize the use of a legacy authentication protocol. We all know that NTLM is an authentication or an old authentication protocol. Most or the commonly used authentication protocol in networks, especially in domains, the Kerberos protocol. So here, Mike, I know our security team is trying to disable NTLM in favor of Kerberos. That's the common goal. NTLM is an older authentication protocol with security limitations. Windows use Kerberos by default in Active Directory environments, but NTLM is still used in certain scenarios. The case involved identifying which applications were still using NTLM authentication. Let me show you how to set up NTLM auditing and use Procmon to identify the exact applications. So this is the case. First of all, we need to enable NTLM auditing through group policy. We need to go to enable NTLM auditing. This will be done using a group policy through in an Active Directory environment, and actually this can be also activated through using local group policy. Let me show you. If I go there and tell him run gp edit, okay, and then open like that, and then we open the section concerning, I think, Windows setting, and then we go to the security setting. Then I think we can go to the local, okay, I think go to security options. Then we have here network security. As we can see here, this is the section of network security. If you double click, now we have let me see which one. This is one, audit NTLM authentication in this domain, audit NTLM. So we have restrict NTLM security, restrict LTLM. So we have here a lot of things concerning restrict NTLM. This is the one we need to add server. Let me see here, NTLM audit authentication in this domain. So this is not the one. So here it is, audit NTLM authentication in this domain. And we have another one, outgoing NTLM traffic to remote servers, this one, okay. And we have another one which is audit incoming NTLM traffic. This is it. So we can see these are the things that we need to activate so we can audit the NTLM authentication. Auditing here means recording everything that is done using the NTLM protocol. This will be recorded and put in the event viewer. So now we have all of these enabled. Okay, as we can see now, we can continue our case. When editing enabled, Windows records NTLM authentication events in the event viewer, Windows event viewer. On a domain controller, you would see events like this. For example, this is event 8004, domain controller blocked audit NTLM authentication to this domain controller. we have seen, for example, I think this user is authenticating to the file server. This is the domain, this is the workstation, this is the user, secure channel 2. So let's see here the explanation. This shows that user 3 authenticated to file server from workstation Win7 x64-0 using NTLM. On the server, you would see the event ID 8003 and on the client event 8001. But here is the catch. When using SMB file sharing protocol, the events don't identify the actual client application. They just show system process PI4. This is where process monitor comes in. So here we know that uh, that there is an NTLM authentication done to the file server, but it doesn't show us if this authentication is done through application through what. So what asked for NTLM authentication? If this a normal file and print sharing, so the user authenticated using NTLM, or this is another thing. So let's see here how we can identify the program that asked for the NTLM authentication. Exactly. In process monitor, you would set a filter for paths beginning with the server name or IP address. So I think we need to put the procmon or process monitor on the file server, okay, and begin monitoring. This shows all attempts to access the server, and by comparing timestamps with NTLM audit events, you can identify which application is causing the NTLM authentication. So let's again try to re-explain that. So exactly, the process monitor will set a filter for passes beginning with the server name or IP address. So we need to put, I think, the procmon on the file server, okay, and then filter the events to the file server itself, the machine. This was attempt to access the server, and by comparing timestamp with NTLM audit events from the domain controller, you can identify which application is causing the NTLM authentication. So here, for example, after doing that, we can filter this, the process explorer or the file explorer, create file. So this is normal because this is an operation, a user trying to access a shared folder on the file server. So the one that is asking for authentication is the explorer.exe. So this is very, very straightforward. So I think the procmon should be put on the file server. So this example, Windows Explorer was the application using NTLM. That's correct because the user is opening the Windows Explorer. So he is, for example, opening this PC, okay, and then he will go to the, for example, section here for the network, for example, and then try to access the shared folder, okay. So this is called Windows Explorer or Explorer. So this process, when he double click, they need to be authenticated to the shared folder or to authenticated to the file server to access the shared folder. This is done using NTLM. Okay, so this is a very, very straightforward case. So yes, this is the particular case. They found Explorer was causing NTLM events by browsing file shares using an IP address instead of DNS name. Using IP address forces NTLM because Kerberos requires DNS names. By correcting this and addressing other findings from the audit, they could gradually reduce NTLM usage and eventually disable it. So this is a great thing. It's a great stuff, sir. I have learned so much over those 2 days. I am starting to see why we rely on Sysinternal tools so heavily for troubleshooting. Okay, so this is the case of the, it's called, let me show you the case names. So here we can, it's called the case of the unknown NTLM authentication or communication. This is case number 43. If we go to continue with the broken Kerberos delegation, this is case number 44. I think I have already this case already explained. The broken case, let me go there. Here is the case of the broken delegation part 4. So here let's go to the first case. We have now case number 44. It's called the case of the broken Kerberos delegation. So one for the NTLM authentication protocol and one is for the Kerberos protocol, especially the delegation. We have seen that we can delegate, or the Kerberos delegation concept is to uh, uh, delegate a service to authenticate on behalf of a user. This is the something here. Let's see this. This one involves application development troubleshooting rather than typical user support. So sysinternal tools work for developers too. Definitely the same tools that help us troubleshoot system issues can help developers debug their application. In this case, a developer had been working on a Windows communication framework client to server program for managing digital certificates. After a few of trial and error, he finally got a got a working version. To make it deployable, he created a new clean project with just the essential code. But then something strange happened. The clean version failed every time with a cryptographic error, while the original version still worked on the same systems. So here, let me see the case. That sounds frustrating. Did he check the code for differences? Yes, he carefully compared all the relevant client and server code, but couldn't find any significant differences. He also verified that the firewall setting and application configuration were correct, that when he returned to process monitor, that's when he returned to process monitor. So he doesn't know where is the error. Let's set up a sample example to illustrate how subtle differences in authentication can be detected. So now we'll open Procmon. Then the developer captured traces of both the working and failing versions of the certificate he is trying to create. Then compare them side by side. Initially, nothing obvious stood out, so he started focusing on a specific aspect like the DLL being loaded. So now here he is opening the process monitor. He is filtering by operation. Is load image include? I think here he is trying to see the signature. Let's see that the filter dramatically reduced the events to examine. When looking at the sequence of DLL loaded by each version, he found a critical difference. So I think load image here, I think is relating to maybe the version, okay, or something. Operation is load image. Okay, let's see this one. So you will see the DLLs working version. This is the certificate manager, so and so. Operation load image. So I think he is focusing upon the load image operation. This is, I think, loading the certificate maybe or something. This is the working version. As for the failing version, seems to be they are loading different DLL files. Okay, so here, so one version was loading Kerberos and the other was loading MS, so and so. What's the significance of that? That's the key insight. Kerberos DLL implements the Kerberos authentication protocol, while this implements NTLM authentication. The application depended on Kerberos constraint delegation, which lets one service impersonate a user to access other service. This only works with Kerberos authentication, not with NTLM. So this is a good thing. I see. So even though the server was correctly configured for delegation, the clean version wasn't using Kerberos at all. Exactly. When the developer checked the client configuration files again, he realized that while cleaning up dead code, he accidentally removed the service principal name. Yes, without SPN, the client defaults to NTLM instead of Kerberos. This is very, very correct. We have discussed, by the way, the Kerberos delegation and the NTLM in this series. So this seems to be the case. He has already removed the SPN for the service, so now he cannot delegate, or the service cannot talk on behalf of the user. Okay, this case shows how process monitor can help identify the subtle differences in the program behavior that aren't obvious from reading code or configuration files. That's impressive. I wouldn't have thought to look at which authentication DLL was being loaded. That's the power of methodological troubleshooting. Sometimes we need to examine things from different angles. Let's move to the case. So first, let's uh, see this case. I need it to be explained in a different way. Let's go there and okay, let's see. Okay, let's go like this one and try to copy. I think I need to let's see this. So we go there and tell Grok explain this case in layman terms and include glossary for terminologies. Okay, if we do like this and put this one, so let me see here this one, let me wait for a moment. Okay, so we copy like this and go like this, Control V, and then this one, and then we can go further like this, and then we can copy and go there, then Control V, then Shift Enter, and then we go to this one, copy, and here you go, Control V, then Shift Enter, and then we can continue with the case, copy, and then we can go like this and Control V, then Shift Enter, then we can go to this one, copy, and then paste, then Control V or Shift Enter, then we can take all of these, okay, so this is the last of it, so we copy and then put like this in Control V, then we can do like that, then we can explain the whole case, Control C, then tell him think and do like this, and then go to ChatGPT, do the same, and tell him enter, and then go to Gemini and do the same. So until they finish, we have now the last case we'll discuss today concerning the cases provided uh, by Mr. Mark Roselbich, the proc dump memory leak. So let's see if we can have this case from here. We have the proc dump, the process killing feature. I think this is not. We have, okay, so I think this is not here. So we have all of these. Okay, let's go and see the other cases. So now we can go there and try to see this one. We have, okay, we can have now some cases. The broken, the runaway, the strange, okay. Okay, so I think here the strange crash dump. No, I think all of these are not. It's called the broken, the proc dump. Let's see here which cases we have. So okay, this is not there. If you go there and try to get from the beginning, I think it's in the first case. If we go there and try to see the cases, so we have, we go, we have let's go and continue. Now we have, let's wait for a moment. Okay, let's wait and see. I think. Okay, let me try to search here with find in page. Now we have the proc dump memory leak, and then try to see this one here. Control V. I think it is there. Let me see here. So let me try to see this. Yes, this is the first case we have here in the first explanation. So we have, let me see now, we have uh, so let's go, let's continue here. Okay, let me just prepare the case. Okay, okay, senior, okay, startup. So malware, slow project file open. Okay, this is something else. Senior, okay, the blamed. Okay, the case. Okay, so okay, here is the case. Okay, let's try to see what it's about. But before that, let's try to read the explanation of every one of these. First of all, let me try to read out using or the grok explanation of this case. So here you go. Let's try to read it out loudly. So here you go. We can read it out loudly.
Imagine you're a developer building a program that's like a digital librarian managing special ID cards called digital certificates that prove who people are online. You've been working hard on this program using a tool called Windows Communication Framework, WCF, which helps different parts of the program talk to each other securely. After a week of tinkering and testing, you finally get it working perfectly. High five. Now, to share it with others, you decide to make a neat, simplified version with just the must-have pieces of code. But when you test this clean version, it crashes every time with a confusing error about security, cryptographic error, even though the original version still works fine on the same computers. What's going on?
So let's try to read the rest.
This is the story of the case of the broken Kerberos delegation, and it's all about figuring out why the clean version failed. Let's break it down step by step in simple terms. The mystery. Two versions, one works, one doesn't. The developer was puzzled. He checked the code in both versions, line by line, but couldn't spot any big differences. He also made sure the computer's firewall and settings were the same for both. Everything seemed identical, so why was the clean version breaking? To solve this, he turned to a detective tool called Process Monitor, which is like a magnifying glass for what's happening inside a computer when a program runs. The detective work, using Process Monitor. Process Monitor watches everything a program does, like which files it opens or which helper tools it uses. These helpers are called DLLs, short for Dynamic Link Libraries. The developer ran both the working version and the failing version of his program, while Process Monitor took notes. Then, he compared the notes side by side. At first, it was a mess of information, so he zoomed in on one thing, the DLLs each version was using. He set up a filter in Process Monitor to only show when DLLs were loaded, kind of like tuning out background noise to hear a specific conversation. And there it was, a clue. In the working version, the program used a DLL called Kerberos.dll, but in the failing version, it used a different one called MSV1_0.dll. This was the aha moment. The culprit, wrong key for the lock. Here's where it gets interesting. The program needed a secure way to prove its identity to another part of the system, like showing a special key to unlock a door. The Kerberos.dll provides a modern, super secure key called Kerberos authentication. The program relied on a feature called Kerberos constrained delegation, which is like giving the program permission to use that key to act on behalf of someone else, but only if it uses Kerberos. On the other hand, MSV1_0.dll uses an older, less secure key called NTLM authentication. The problem? NTLM doesn't work with Kerberos constrained delegation. It's like trying to open a high-tech lock with an outdated key. So, the working version unlocked the door fine with Kerberos, but the clean version kept failing because it was stuck with NTLM. The mistake: missing instructions. Why was the clean version using the wrong key? The developer went back to the program's instructions, called client configuration files, and found the answer. When he simplified the code, he accidentally deleted something called the service principal name, SPN. The SPN is like a label that tells the program, hey, use the Kerberos key for this job. Without it, the program shrugged and defaulted to the old NTLM key instead. The fix: putting the label back. Once the developer realized the SPN was missing, he added it back to the clean version's configuration. Suddenly, it started loading Kerberos.dll again, used Kerberos authentication, and worked perfectly, just like the original. The lesson: small details matter. This case shows how a tiny change, removing the SPN, can cause a big problem, and how a tool like Process Monitor can help spot differences you'd never catch by just reading the code. It's like finding a needle in a haystack by focusing on the right clues.
So as you can see here, very, very good explanation. Okay, very, very good explanation. Let's go to ChatGPT and see his answer. So if you go and try to read the answer, which is very, very short actually.
Key story in everyday language. A software developer had two versions of the same certificate management program. Original version worked perfectly. Clean version, the exact same code copied into a fresh project so it would be easier to ship, but it always crashed with a cryptography error. After double-checking the code and firewall settings, he still couldn't see why the clean copy failed. So he used Process Monitor, a tool that watches every file, registry, and network action a program performs. By filtering the trace to show only the DLL library files each version loaded, he spotted one crucial difference. Version: DLL loaded for authentication. Working: Kerberos.dll. Failing: MSV1_0.dll and TLM. The program depended on Kerberos constrained delegation, a feature that allows one service to pretend to be a user when it talks to another service. That feature only works if Kerberos authentication is used. In the clean project, the developer had accidentally deleted the line in the configuration file that specifies the service principal name, SPN. Without an SPN, Windows falls back to the older NTLM method, so the program loaded MSV1_0.dll instead of Kerberos.dll, and delegation broke. Re-adding the SPN entry made the clean version work again. Key takeaway: sometimes two programs look identical, but a tiny missing setting can silently switch them from Kerberos to NTLM. Watching which authentication DLL gets loaded is an easy way to catch that mist.
Actually, this explanation is not that good, by the way. So I think let's see Gemini and see if he also can explain it in simple terms. Okay, let's see this.
Reading the instructions. Glossary of terms. Application development. Okay, let's break down this technical case into simpler terms. The simple story. The case of the broken security badge. Imagine a developer built a special intercom system, the WCF client-server program, for managing secure ID cards, digital certificates. The working version. The first version worked perfectly. It used a high-security communication method, Kerberos, that allowed one part of the system to vouch for the user when talking to another part. This special vouching is Kerberos delegation. Think of it like using a special company ID badge, Kerberos, that has extra permissions written on it, delegation. The cleanup. The developer then decided to tidy up the system's instructions, code, to make it neater, clean project. They removed stuff they thought wasn't needed, dead code. The broken version. Suddenly, the cleaned up version stopped working. It gave a confusing security error, cryptographic error. The original, messy version still worked fine on the same computers. The detective work. The developer was stumped. The instructions looked the same. So, they used a special detective tool, Process Monitor, that watches exactly what a program does step by step, like which tools it picks up. The clue. By watching closely, the developer noticed something tiny but crucial. The working version picked up the tool for the high-security badge, Kerberos.dll. The broken version picked up the tool for a simpler, standard security badge, MSV1_0.dll, which handles NTLM. The problem found. The special vouching trick, Kerberos delegation, only works with the high-security badge, Kerberos. The broken version was trying to use the standard badge, NTLM, which didn't have the necessary permissions, so the system failed. The mistake. Why did the clean version use the wrong badge? When cleaning up, the developer had accidentally removed a critical setting, Service Principal Name, or SPN. This setting was like a label telling the system, hey, use the high-security Kerberos badge for this. Without that label, the system just defaulted to the standard NTLM badge. The lesson. Even tiny changes like removing one setting you think is dead code can break things in hidden ways. Tools like Process Monitor are powerful because they show what's really happening under the hood, helping find problems that aren't obvious just by reading the instructions. Glossary of terms. Application development.
So as you can see here, I think the best explanation is from Grok, then the second one is Gemini, and the least one is ChatGPT o3. So let's go to the last case, which is the case of ProcDump memory leak. The developer noticed ProcDump itself was leaking memory. So they open ProcDump, which is a program for capturing memory dumps. They saying that it is using a lot of memory. So when they are trying to capture a dump using ProcDump, they see that it is using a lot of memory. They used VMap, another program, to see why it's taking a lot of memory. Okay, to track back to the source. First, let's simulate a basic memory leak with a simple PowerShell script. So this is if you want to simulate a memory leak or a high memory usage. This is the script. Okay, and you can do this. Now let's use VMap. This is a utility to analyze your virtual memory. Okay, I think also the physical memory. So here how you can use the utility. Okay, she is opening the utility and trying to get something called memory leak. VM map shows a detailed breakdown of memory usage by type. You can see the private memory growing over time. In the real case, they use the timeline feature to select a period of memory growth. Then clicked on the heap allocation to see all stacks responsible. Okay, so this is how they are analyzing the using of memory, snapshot, so and so, working so and so. So it is increasingly, I think it's this is to about 20 seconds or about something, and it's increasing the private bytes and the working bytes. I think this is something related to the memory. Okay, by selecting the memory regions that were growing and looking at the call stack, they traced the leak to a specific line of code in ProcDump that was allocating a buffer but not freeing it. That's incredible. So they could pinpoint not just the leaking process, but the exact line of code causing the leak. Yes, when you have simple files configured, VMap can even show you the source code line that allocated the memory. In their case, it was a function called wildcard search that allocated memory for string conversion but never freed it. So these tools are much powerful than I realize. I'm eager to try them in real troubleshooting things. So let's try to just maybe re-explain it again in simple terms. Let me try to uh, make it more simpler. Uh, where is okay? Let's hear this one. Let's wait for a moment. No, let me just try to get this one. Okay, so here it is. But first, let's try to do something here. We can go and take the first thing here. Then we can copy and put something like this, and then go and copy. Okay, and then put this here, and then shift enter, and let's get the script and put it here, control V, shift enter, and let's continue with this one. Copy, then we do like this and put like that, and let's copy this one. Okay, and then put it here, control V, shift enter, and then let's do like this. We can copy and then paste again, control V, and then let's what does it happen here? Just a moment. No, this is not control Z. Okay, so this is not the case. So I think I have to take a lot of it. Okay, so let's wait for a moment. This is the thing. So here we have this, copy, and then do like this, paste, then shift enter, and then we can go and copy these two, and then put it back here, control V, then shift enter, and then so this is the last of it. So here you go. Now you can go and take the last, you copy and then paste, and then close the brackets, control A and then control C, and then let's see how Grok will explain it. Now we can go to ChatGPT and do the same. Okay, and go to Gemini and do the same. I think here, I think I have already finished the limit. Okay, we can try to use Google Studio, and then can try to do that, as for chat, and then try to do this, control V, and then to do that. Now let's see the answer of Grok. So this is the case. Let's try to read it out loudly. Now we have the explanation of this case. Okay. Okay. We can read it out loudly.
All right, let's dive into the case of the proc dump memory leak and break it down in a simple, everyday language. This is a story about how developers figured out why a tool was misbehaving and fixed it using some clever detective work. Imagine a tool that's supposed to help you, but ends up making a mess instead, like a vacuum cleaner that leaks dust while it's cleaning. That's what was happening here, and we'll walk through how they solved it, step by step. At the end, I'll include a glossary to explain any tricky terms in plain English. What went wrong? The star of this story is a tool called ProcDump. Think of ProcDump as a photographer that takes pictures of what a program is doing when it crashes or acts strange. It's super useful for figuring out problems. But in this case, the developers noticed that ProcDump itself had a flaw. It was leaking memory. A memory leak is like forgetting to clean up after yourself. When a program uses memory, a bit like borrowing space on your computer to store stuff, it's supposed to give that space back when it's done. If it doesn't, like leaving dirty dishes in the sink forever, the computer's memory fills up and things slow down or crash. That's exactly what ProcDump was doing, and the developers needed to find out why. Step 1. Making a fake leak to test things. To show how they tracked down the leak, Sarah, a senior tech in the story, created a simple example using PowerShell, which is like a command tool for Windows. She wrote a little program, or script, that mimics a memory leak on purpose. Here's what it does. Every second, it grabs 1 megabyte MB of memory, like reserving a small box to store something. It tosses that box into a big pile, a list, but never throws any of the boxes away. So the pile keeps growing, 1 megabyte, 2 megabytes, 3 megabytes, and on forever. This fake leak helps us see what a real one looks like. In the script, you'd see messages like text, copy, allocated 1 megabyte, total, 1 megabyte allocated 1 megabyte, total, 2 megabytes allocated 1 megabyte, total, 3 megabytes. And it just keeps going. This is a perfect setup to test their tools. Step 2. Calling in the memory detective, VMMap. To catch the leak, Sarah used a tool called VMMap. Picture VMMap as a super smart magnifying glass that shows you everything a program is doing with the computer's memory. It can tell you how much memory the program is using, what kind of memory it is, like private memory, which is space only that program gets to use, where the memory is being taken from. When Sarah ran VMMap on her fake leaky program, she saw the private memory growing bigger and bigger over time. That's a red flag, a sign that the program is holding on to memory it should let go of. Step 3. Watching the leak happen live. In the real case with ProcDump, the developers used a special feature in VMMap called the timeline. Think of this as a rewind button that lets you watch how memory usage changes over time, like a security camera replaying footage. It looked at 2 moments. At 9 hours, 50 minutes, and 23 seconds, the program was using 253.4 megabytes of private memory. At 9 hours, 50 minutes, and 53 seconds, 30 seconds later it jumped to 283.4 megabytes. That's an extra 30 megabytes in just 30 seconds. Imagine your phone's storage filling up that fast with junk. It's a clear sign of a leak. Step 4. Following the trail with call stacks. Here's where the magic happens. VMMap doesn't just tell you memory is leaking. It shows you why. It does this with something called call stacks, which are like a map of what the program was doing when it grabbed the memory. Imagine you're following footprints in the snow. Each step, or stack, shows you which part of the program led to the next, all the way to the spot where the memory was taken. In the ProcDump case, the developers followed these footprints and found the culprit, a function called wildcard search. This function was grabbing memory to do a job, like converting text, but it wasn't giving the memory back when it was done. It's as if you borrowed a friend's bike and rode off forever instead of returning it. That memory kept piling up, causing the leak. Step 5. Fixing the problem. Once they knew the exact spot in the code causing trouble, fixing it was simple. They updated the wildcard search function to free the memory after using it, basically telling the computer, I'm done with this, you can have it back. In programming, freeing memory is like cleaning up after a party, so the space is ready for the next event. With that change, the leak stopped. Why this matters? This case is awesome because it shows how tools like VMMap and ProcDump can turn a confusing problem into a clear solution. They didn't just guess what was wrong. They zoomed in on the exact line of code, like finding a needle in a haystack with a metal detector. And when you add symbol files, extra info that links code to readable names, it's even easier to see what's happening.
So this is the explanation. Very, very good actually. Let's see the explanation of ChatGPT, and let's see if it is useful. I think uh, Grok is very, very good at simplifying topics or subjects. Okay, I think this is good. I see Gemini, and Gemini is not that good. Grok, ChatGPT is not that good. I think maybe Claude is near, but I think Grok maybe is the best. But let's try to read this explanation as well.
The story in plain English. A strange problem appears the team that writes the Sysinternals tool ProcDump noticed something ironic. Every time they ran ProcDump for a while, it started eating more and more memory, eventually slowing the PC. That behavior is called a memory leak. A program keeps grabbing RAM, but never lets any go. Recreating the leak on purpose to show their junior teammate how to hunt leaks, Sarah writes a tiny PowerShell script that allocates 1 megabyte of memory every second and never releases it. The numbers on screen climb. 1 megabyte, 2 megabytes, 3 MB. Watching the leak with VMMap, they open VMMap, a sysinternals tool that draws a colorful map of where a process's memory goes, code, data, heaps, DLLs, etc. The private bytes and working set graphs rise steadily, proof the script is leaking. Map's timeline lets them pick two snapshots 30 seconds apart. The difference report shows an extra 30 megabytes of heap allocations. Zooming in on the culprit in the real ProcDump case, the developers ran VMMap against ProcDump itself, selected the growing heap region, and looked at the call stacks, the list of functions that led to each allocation. With symbol files loaded, VMMap could resolve those addresses to actual source code lines. They found that a helper function called wildcard search was creating temporary string buffers but never freeing them. Every run left a little more RAM stranded. Fixing the bug after they added the missing free this buffer line, ProcDump stopped leaking memory. VMMap confirmed it. The private bytes graph flattened out. Why it matters? Memory leaks can be maddening because nothing crashes. You just run out of RAM hours later. Tools like ProcDump to capture dumps and VMMap to visualize memory let you see exactly which parts of the program keep growing and trace them back to the offending code, saving huge amounts of guess and check time.
So this is not a good explanation from my point of view, but let's first see what is working set, the subset of private bytes that is currently in physical memory, not just reserved. The subsets of private bytes that is currently in physical RAM, not just reserved. Okay, so the total memory process has reserved that only it can use. So there is a reserved memory and not used, and the working set is the actually used memory. So for example, maybe the program is reserving 3 gigabyte for its use, but it's only working with one. So this is the difference between private and the private bytes and working set. I think actually this explanation is not that good. If we go to Gemini and try to see the explanation here, uh, I think the explanation seems to be uh, mm, fake leaking using so and so call feature before timeline. And okay, I think we can read it just to see if there is any differences between what is said by uh, ChatGPT and Grok, just to make it more simple.
Okay, let's break down this technical troubleshooting story in a plain English. The simple story. Imagine your computer's memory, RAM, is like a temporary workspace or a set of drawers. Programs need to borrow space from these drawers to do their work. When they're finished with a piece of information, they're supposed to put it back or tell the computer they don't need that space anymore. A memory leak is like a program that keeps borrowing space from the drawers but forgets to give it back. It keeps taking more and more space, never cleaning up after itself. Eventually, all the drawers get full and the computer slows down or crashes because there's no workspace left. In this case, a program called procdump, which is ironically often used to help find problems in other programs, had its own memory leak. It was filling up the computer's memory drawers without tidying up. How they found the leak, the detective work. Making a fake leak. Sarah, the senior person, first shows Mike, the junior person, how a leak works. She writes a tiny instruction list, a PowerShell script, that deliberately creates a memory leak. It keeps asking for 1 megabyte chunks of memory space every second and never gives them back. This is just to demonstrate the problem clearly. Using the memory X-ray, VMMap Sarah then uses a special tool called VMMap. Think of VMMap as an X-ray machine for a running program's memory usage. It shows exactly how the program is using the computer's memory drawers, what kind of space it's using, and how much. Watching the leak happen, they point VMMap at the fake leaking script. VMMap shows that the amount of private memory used only by that script, is growing and growing over time. Using the time machine, Timeline VMMap has a cool feature called Timeline. It's like taking before and after snapshots of the program's memory usage. By comparing the snapshots, they can see exactly which parts of the memory grew the most during that time. In the example, the private memory grew by 30 megabytes in 30 seconds. Following the breadcrumbs, call stacks, when VMMap highlights the memory areas that grew, it can often show a trail of instructions, the call stack, that led to that memory being borrowed. It's like following breadcrumbs back to see who asked for that piece of memory. Pinpointing the problem code. In the real case with procdump, not the fake script, the developers used this technique. By looking at the growing memory in the timeline and examining the call stacks associated with it, they followed the trail back. Because they had symbol files, like a decoder ring that links the computer's code back to the original human-written code, VMMap could point them to the exact function, wildcard search, and even the specific line of code within procdump that was borrowing memory but forgetting to return it. In short, they used a memory analysis tool, VMMap, with its timeline feature to watch how procdump's memory use grew over time. By examining the call stacks, the trail of instructions, linked to the growing memory, they traced the leak back to the precise line of faulty code.
So as we can see here, very, very good explanation concerning this case. Again, the private memory, the amount of memory that specific process has allocated for its own exclusive use and cannot be shared with other processes. A steady increase in private memory often indicates a memory leak with that process. Working set, the subset of process memory currently held in the computer's physical RAM. The fastest memory chip memory not in the working set might be swapped out to the hard drive. Currently held in the computer physical memory not in the working set might be swapped. Uh, okay, anyway, so this seems to be a good explanation. So these are the 45 cases that we are currently explaining it across about maybe 14 or 15 videos. Let me conclude, or let me show you how you can get all of these cases in a video format that is explained by Mr. Mark Rosenberg. Let me get you Mark Rosen Rosenbich. Okay, this is it. Here is the website. He's a channel, and we tell him I will subscribe actually. And then we have the playlist. So now we have all of these cases, I think, are explained in the case of the unexplained. So we can see here all of these cases are explained. We can see maybe some of them are during the years. So we have 2008 until 2016. Okay, I think let me do something. I will try to do something here. I'll try to go to Notebook LM and try to summarize all of these cases through his video. Okay, I'll try to do that, but from this, let me try to get each case one by one. So I think this is the first case, so we'll copy it and try to put it here, YouTube, and then we will add this one, Control V, and insert it, and then we will add the next case. So let's do that. We'll copy this one again and try to add, and again can add the YouTube, again this one, and then add it, insert. Then we have the second case, then we have the third case.
Technical fellow, the highest technical.
And take it like that, copy. And this is the third case. And let's go like this and add it to the links. And then we have all of these. We will go to the fourth case and try to take it. I will try to make a summarization for all of these cases. Let's hope we can make it in a better way. So we have the fourth case, and then we have the fifth case. Now we'll copy like this one, and then we'll put the fifth case like this one. Okay, and then we have the fifth case, then we have the sixth one.
Give me a little more time.
Then we have copy. Okay, and put like this one. Okay, then we have like this one, then Control V. Okay, now we can go to the 2013 case. Okay, copy. Then we add like this. Okay, so we'll do like that. And here you go. Now we have case number 424 or 2014.
Okay, so the jokes are going to be good.
Then we'll copy all of this, 2014. Then we have the sources, 2014, insert, and then we have 2015. Okay, then we have two other cases left. 2015. We'll do like that. Okay, and like this, and then we can go to 2016.
All right.
Just try to summarize them as far as I can. So now we can, I have already explained them, but let's see, maybe he have added anything else in his broadcast. Okay, we go to the last one, which is 2016, and then we have this one, copy. Okay, and then paste the last one. Okay, and then put the website or put the YouTube link, and then we have add all of them. Okay, what is this? Escape is not available anyway, so we will remove that source. Okay, and then we can refresh. So we have 10 sources. Okay, as you can see here, these are real world scenarios. When first of all, we need to first make a podcast. First of all, let me see if I have my Arabic. This is English, so let's generate a podcast. Okay, and see if it can get us some summarization of all of these cases. Okay, let me see. When it finishes, I will return back, so let's wait for a moment. So let's continue, guys. Let's see. I will try to download first this this podcast and put it in this one, and then we can try to create a couple of things. First of all, we need to have a study guide. Let's try to see. And we'll have a mind map, and we have a lot of things actually. So this is to be our reference. Okay, we have already a study guide, and then we have frequently questions and answers. So we can do a lot of summarization and focusing upon uh, these videos concerning the cases that we have explained through the AI. So you can take this like a reference and take my explanation as another reference, okay? Because I think he is explaining the same, but maybe he is adding other things, but I've tried to explain it through the AI tools. So we have frequently questions and answers. Now we have something like the briefing documents. So all of these are things that will help us to explore these videos without opening them one by one, okay? And then we have the last thing, we have the timeline, okay? So this is how you can do this. You can go to Google and do a lot. I think actually I can share all of this workspace. I will share them for you guys. You can go and see everything through it. You can see this is like our source. You can see the videos, okay, and you can see a lot of things actually through it. So let's go and see what is remaining. Now we have all of these generated. The last thing I need to focus on, which is a mind map. So now let me open the mind map just to get it more simple. This is troubleshooting Windows problems. We have CentOps, okay, sluggish performance, error messages, application hangs, blue screens of death, buggy things, the core concept. We have processes, threads, so each one of these are explained. We have the process, we have the container, the asset space, track resources, security profile, contain one or more threads. So these are all, I think, it is explained through Mr. Mark Rosenben's videos. We have the thread. Okay, so all of these are explained. System processes. Okay, call stack. Okay, all of these are this one. Function. Okay, and now we have debugging tools for Windows. We have a lot of things. So we can see here this is a lot of things, and we have the troubleshooting techniques. Now we can see this is are all, I think, explained by Mr. Mark Rosenben. We have when in doubt, run process monitor, analyze crash dumps, look at thread stacks, look for third-party DLL. So I think this is a very, very good thing. I will share this workspace for you guys. Let's go and see, for example, the study guide. Let's see if it will contain something. So here he is giving us some question or quizzes. Okay, quizzes, question and answers, essay format, so glossaries. So I think this is good thing to see. This is for the study guide. As for I think the question and answer, here you go. This is the question and answer things. What are the common symptoms of unexplained Windows problems? Unexplained Windows problems can manifest in various ways. Users often report sluggish performance where the system feels less responsive than expected. Okay, so as we can see here, a lot of questions and answers to tell us or to explain what the videos are saying in a question and answer format. This is it, and then we can go to that. I think this is the timeline, maybe. Okay, I think this is the timeline. So here we can see a lot of things. We can see here a lot of things, important ideas and something. So these are all things we can see here. This is like a timeline. Just a moment, guys. Just a moment. So let's continue, guys. Here is my Telegram channel. I will put the link for this this workspace. Okay, now I can see the owner. I can copy the link. Okay, here you go. Add people or group. Should I add something here? I don't know if this could be the case. Okay, I think I cannot share it. I need to share it with a certain email address or certain group of people. Okay, so I will just try to put all of these text files, okay, in or all of these notes. I'll try to upload it to my Telegram channel, but before that I will add all of the cases generated by Claude 3.7 Sonnet, the 45 cases that were explained in the previous videos. So it will be all on the Telegram, so you can see them and read them. And with the podcast, so also I will upload this podcast on my Telegram channel. So just wait for a moment. So here you go. These are all of the cases and the podcasts. Think of this like a summary. Okay, so let's put them all. So all of these cases are in MD or Markdown file, and as for the podcast, it is in WAV file. Okay, so now I am uploading it one by one. So let me try to see if we can have all of these notes added. So first of all, this is the guide. We need to so this is like this. Let's try to convert to a source, so we can put it there. Okay, as we can see here, it will be converted to a source, so we have it in the sources. Now we have the second thing also as a source, convert to a source. Now we have this, so all of these are added to our sources. Okay, and oh, this is added, so we have this also added as a source. And now we have the third one as a source, convert to a source. Okay, and now it is added. And we have the fourth one. I will try to copy them later, convert to a source, and now we have it already converted. And as for the mind map, you can download it, okay, but this will be not interactive, okay. It will seems to be, so if you go have a broader look, if you let me make it less, so we have all of the videos in a mind map. We have blue screen of this, for example, protect data triggered by kernel mode error call, bug function. So all of these are something related to blue screen of this. And we have malicious concepts, so we can see here a lot of things. So as we can see here, this is like a revision or like a summary for what is explained in Mr. Mark Rosenberg's videos. So you can download it. I can download, but it will be not that good. But anyway, you can see the podcast. It will be something good. I'll try to export the sources, okay, in any way, and try to upload it to my Telegram channel. As now I have all of the cases used, for all of the cases downloaded. As for the podcast, let me try to show you a part of it, but it's about 29
Ever get that feeling your
minutes.
computer's just, I don't know, got a mind of its own? Like it's deliberately slowing down.
Oh, definitely. Or your favorite app just hangs mid-task.
Exactly. Or you get those completely cryptic error messages. We've all been there, right?
It's super frustrating. You need these things to work, and when they act up without any clear reason, well, you feel kind of lost. Like, what's actually going on under the hood?
Well, today we're going to try and shine a really bright light into that darkness. We're doing a deep dive into troubleshooting common Windows issues.
And we'll be using this amazing suite of tools called Sysinternals.
Think of them as like the ultimate Swiss Army knife for your Windows system. They were created by Mark Rusinovich and Bryce Cogswell, brilliant folks.
Right. And for you listening, if you want to get up to speed quickly and really understand this stuff, this deep dive is pretty much designed for that.
Yeah, we're not just talking theory here. We're going to take real-world examples, actual computer mysteries,
and dissect them using these Sysinternals tools to see exactly how they were solved.
These aren't made-up scenarios either. These are genuine head-scratching problems that the creators, Mark and Bryce, and loads of other users have actually faced.
And solved using these techniques.
So consider this.
So this is it's about 20 or half an hour podcast. This is try to summarize all of these cases, okay, explained in the videos. If you need to see them, you can download them one by one and listen to them, but actually this is like a summary. You can go and download them and read them, and you can also read the markdown files I have already put for you guys. And this is not an example, or this is not the case, the real case. This is re-explained by the Claude 3.7 Sonnet AI tool, which adds a lot of things to the case itself, some PowerShell scripts, some additional explanation, okay. You can see them from here, or see them from the podcast, or you can read them from the PDF of Mr. Mark Rosenberg. We have seen this before. This is the PDF of Mr. Mark Rosenberg. So here you go, this is it. As you can see, this is also, you can use it to read as a source. As we can see here, all of these things. And actually this part, troubleshooting the case of unexplained, as we can see here, this is this chapter is this as the same name as his play or playlist in YouTube. So I think this is the theoretical part, and this is the practical part maybe. So you can read it from an alternative sources, and this concludes for our series as a whole. Okay, guys, so I hope you all enjoyed the journey concerning the different troubleshooting aspects or topics: troubleshooting Active Directory, troubleshooting Windows operating system, troubleshooting DNS, troubleshooting group policies, troubleshooting using Event Viewer, troubleshooting using PS tools, or troubleshooting using Sysinternals suite or suite. Hope this series you enjoyed it, as I will. Hope this video was informative to you all, and thank you all for viewing until our upcoming series, which will be it will be like surprise for you guys. It will be a very important topic, and it is very critical to our to most of the IT administrators. Hope this video informative to you all, and thank you all for viewing. Thank you so much.